Okay, so today we're going to be going over basic data structures. So first of all, we're going to go over the definition of data structures and what a data structure actually means and what people think of and how data structures are used, what people think of when they see data structures. So it's pretty self-explanatory. Data structures are basically ways to store data in the computer's memory in different formats. Each data structure has its own use. So some data structures might be for like one problem where another data structure couldn't be used, or it would be very inefficient to use a data structure. So it's basically like fitting puzzle pieces together. One data structure would be the right puzzle piece. Although it's not exactly the same, because you can have multiple data structures used for the same problem. It's just that the efficiency of each data structure may be different depending on the problem. So one very common data structure are just arrays, which I hope most people are familiar with. It is actually a type of data structure. People may not instantly think of arrays when they think of data structures, but it is true that arrays are data structures. And again, we're going to be going over this list of data structures. It is a bunch from APCS. Some you may not have gotten to, but yeah, so we're going to go over linked lists, vectors, hash maps, sets and hash sets, stacks, and queues. So first, we're going to be looking at arrays. And most of you are familiar with arrays. I'm just going to go over the definition of arrays again, just in case people have a slightly different conception of what an array actually is. So an array is a list that stores one type of object or primitive. In Python, arrays are called lists, and they can store multiple types of things. So the special thing about Python arrays, as opposed to arrays in other languages, so relevant to competitive computing in C++, is that in Python, arrays are just typed by objects, which means that you don't really care what is in the array. Anything can be in the array. It doesn't matter. But in something like C++, things like ints would have their own array, and you couldn't really have any other type of object. So int, char, string, float, all those things would have to have an array just for themselves. In many languages, in most languages actually, arrays are fixed length, static length, which means that once you create the array variable, you cannot add more than the maximum length of that array. Now in Python, this is not true because arrays are automatically resized to fit how much data they have, which is nice. It's easy to use, and it has its uses, but in a lot of problems, you don't need arrays that resize themselves in competitive programming, which is why C++ arrays are just fine, and they are, in fact, more efficient. So if you don't know how arrays are written in most languages and in Python, this is just an array. It is a one-dimensional vector. So if you have heard vector in problems or in other computer science literature or media, you may be familiar with vectors, but you may not know what they are. Vectors are just arrays, except for vectors can only be one-dimensional. And by one-dimensional, I mean it cannot be something that has more than like a line of information, I guess you could visualize it as. So, so this X is array. In Python, we initialize it to 1, 2, 3, 4, 5. So this array is length 5. It has 5 values, and those 5 values are accessed by index 0, 1, 2, 3, 4, since everything is 0 indexed in most languages. Now, arrays can store any object, as long as it's the same type of object. For instance, in not C#, in C++, you can have arrays of arrays, and that's where you get to dimensionality. So an array of arrays is called a multi-dimensional array. And that is very useful for visualizing and using 2D or 3D or even more dimensions of data. And that's useful for basically connecting different values together and getting data to be in a format that more accurately represents what you want in a problem. So a 2D array can be thought of as a grid or a table. Well, rather, a grid or a table is a really good example of a 2D array, since it basically looks like this, where we have a grid of 9 numbers, and the grid is a 3x3 grid. And if you actually look at this carefully, you can see that this is actually one big array, and in each element of that array, we have another array. And in that nested array, in that child array, we have the actual values, which are in this case 1, 2, 3, and then 4, 5, 6, and then 7, 8, 9. Now, to access a 3D array's value, or sorry, a 2D array or multi-dimensional array's values, you have this notation because you're accessing in here, we're accessing the second index, so 0, 1, 2, which would be this array, and then within that, we're accessing the first index, which would be 7, 8, 9, so 0, 1, that is 8. So as you can see, printing that is 8. If we were to change this to something like 1, 1, that should give us 5. And if I run that, yep, we can see that it is 5. Now, arrays are pretty simple. If anyone has any questions at this point, feel free to ask in the chat. Or even unmute and ask. That's fine too.
Can you increase your font?
Can I increase my font size? Sure. Is that good?
Yeah, that's better.
Okay. So the next thing we're going over, which is very similar to arrays, is linked lists. So linked list is very similar to an array in that it stores values in a sequence, but it does not store the actual values themselves. It stores these things called nodes. You can think of them as objects that have a value and then a reference to the next value. So what this means is that you have a node in this visualization. The node is this thing, this entire box. The value of the node is in the data of the node, which is A. And then the node also contains a next reference, which you can see here. And the next reference points to another node. So basically, by looking at next, you can see the next node. And then that node has its own value and it has another next reference. So you look at that next reference, you go to the next node, so on and so forth, until the next reference is null, which means you've reached the end of the list. As you can see, it's like a chain of links, which is why it's called a linked list. And this linked list here is a singly linked list because each node has a reference to the next node and it's just one single reference. Now, if you imagine that each node had a reference to the next node and the node that came before it, so you could go from B to A and B to C, instead of just B to C, C to D, you could go either direction. That would be called a doubly linked list. Now, the difference, one major difference that you should keep in mind between linked lists and arrays is that a linked list, in an array, the access operation is just this, and it only takes one operation to access the element. Now, if you recall from last lesson, we talked about time complexity. This would be a constant time access operation. Now, in a linked list, to find a value, if you were trying to find C, or if you're trying to find the nth value, you would have to go 0, then if that's not the value, then go to 1, to 2, to 3, to n. So it is a linear operation and it runs O of n. So linked lists are kind of different in that regard. Also, lots of other data structures have access operations that aren't in constant time, but a linked list is probably the most prominent example of that. So if you understand that, that's something that you should understand rather. So if anyone has any questions about linked lists, you can ask. Linked lists are things that we could have implemented. We could have shown an example implementation here, but it would be quite a detour from our lesson. So we decided to, for brevity, keep that out.
We are gonna be, or I am gonna show you guys how to implement one on Thursday. So that's for the Thursday meet, where we're gonna practice how to like come up with algorithms and implementation of these data structures, which I think it's pretty important to know just how they work underneath. And also, like Amit said, this is a linear function, but sometimes if you want to access the head in a singly linked list, that's a constant. Also, if you want to access the tail in a doubly linked list, that's also constant. But addition with this, if you want to like insert it, that's also constant time.
No. Inserting
Inserting
is
constant. No, and with the
yeah.
tail. With the tail.
Yeah. So inserting to the end or to the start of the linked list is constant. Doing operations with the head and tail of linked lists are usually constant time operations, but it is in the middle of the linked list where you get to linear time on average. So next, very important, stacks and queues. So we're going to start with stacks, but stacks and queues are very similar, so they have their section together. A stack is a data structure in which you store objects by following the last in, first out principle. So a really good visualization of this is if you have a stack of books. If you want to add to the stack of books, you add on top. But you don't necessarily, if the stack of books was really heavy, you couldn't just take it up and add to the bottom of the stack. Now, think of it like it was illegal to add to anywhere but the top of the stack. That's exactly what a stack is in computer science. Because we cannot add elements to anywhere other than the top of the stack. Now, taking things off, you also have to take in from the top of the stack. So as soon as you put something on the top of the stack, and then you want to take it off again, you just pop off the top of the stack. These are called pushing. So you push objects to the top of the stack and you pop objects off the top of the stack. Now, that is last in, first out, because the last thing you put in would be at the top of the stack. And then as soon as you took something out, that'd be the first thing to come out. So if anyone doesn't understand that terminology, that is very important to know. So just ask in the chat after the lesson or right now. So just like we have last in, first out, queues are data structures which are first in, first out. Now, queues in real life, I know that people don't generally refer to them as queues, but it is a line, basically, a line of people is what I mean. So the first person to go into line will be the first person to get out of line, because you go from the back of the line to the front of the line. That's why the first person in is also the first person out, which is first in, first out. Just like with queues, just like with stacks and queues, you use the push and pop terminology, which means you push objects to the back of the queue, which would be pushing a person to the back of the line. And then popping objects from the top of the queue would be taking people from the front of the line. Yeah. So stacks, queues, and this other thing called deck, which is a queue that you can pop from either side. It's slightly different than a regular queue, and we won't really be going over the majority of the use cases of decks because it's very similar. So a linked list can be used to implement all three of these data structures internally. We won't be going over, as I said already, we won't be going over that in this lesson. In our Thursday meeting, we'll probably be doing some practice coding and practice implementing that, as Carlos said. So another really, really important data structure here, sets. I saw some people joined late, by the way. So the recording is going to be there, and also you can just stick around afterwards. We're going to be staying for a bit. So next thing is sets. So sets are data structures that are very similar to arrays. You can actually think of them like arrays, but simply unordered, and they don't have duplicate elements. What I mean by this is that in an array, if I scroll back up, we have this array. Now this has a order. We could arbitrarily change these to something like 1, 3, 4, 1, 5, 6, something like that. Now you may think, oh, that's not an order, but that is an order. That's the order we place them in. And the computer remembers that order, since the index 3 will always be 6, the index 2 will always be 1, the index 1 will always be 4. And if I were to insert elements to the end of this list in my program, it would be at the end of the list. It wouldn't be anywhere else than where I said it would be. Now, the problem with, or not the problem, but the difference between arrays and sets is that there is no guarantee that it would be an order. Now, in some programming languages, sets are implemented as ordered lists, and in that case, they are extremely similar to arrays. But in general, you shouldn't really count on sets being unordered, or sets being ordered or unordered. You should assume that they're unordered unless you have searched it up and you have confirmation that this set is in fact an ordered implementation. Now, the more important difference between, or at least in my opinion, the more important difference between arrays and sets is that sets cannot have duplicate elements. And what I mean by this is that adding a 2 to a set that contains a 2 already, as you can see here, adding a 2 to the set of 3, 5, 2, 7 would not change anything, since 2 is already in the set. Now, if we try the same thing with an array, we could still add, for example, another 3, or another 4, another 1, and so on and so forth. We can have an infinite amount of the same amount of objects, and they'd actually be in the array. Now, a set is not like that. Sets are actually very similar to something you might have done in math. Like, it is what you did in math, but you may be familiar with sets from math, like the set of solutions, stuff like that. Set notation in geometry is very similar to set theory in set theory that is used in computer science. So finally, or not finally, but additionally, we have hash sets. So hash sets are, in their name, it's just a set that uses a hash-based implementation. And what I mean by hash is that I didn't talk about it in the article because hashing could be its own multiple of its own lessons, honestly. But the most important part of hashing is that it basically is able to change the access time of your sets to be in constant time no matter what. It is actually called amortized constant time, or OP1, because on average it is in constant time. Now, you don't need to know about hashes. You just need to know that they are a thing and they exist, and that sets and hash sets have a slight difference. But you don't need to really know how it works right now. And if you take APCS, or at least in my APCS class, we did talk about hashing and hash sets, hash maps, etc. So you'll get to this if you want to. You can ask after class, and I'll go into more in depth. Not class, after the lesson. I'll go into more in depth explanation. So if everyone understands sets, that's great. I'll move on to maps. If you have any questions, as always, just ask.
Maybe we can use an example in like
in code.
Yeah.
Sure.
Like that should be really easy to show.
So if I have this array, I'm just going to use this code block here, and I print out x. That, as you can see, that is x. And I think the notation in Python is that. So if I actually do something like this, that will make a variable called xset, which is basically just converting x into a set. And if we look at xset now, which is a set version of x, you can see Python has ordered it for us, and in fact, it has sorted it for us, which is kind of, I guess you could call it unique.
It's really useful for programming, but
Right.
not for competitive coding, where this matters. And like
For a competitive, you normally want an unordered set rather than ordered
which
ones.
is why, like, I think it's pretty important that while we teach in Python, we don't really encourage Python to be used for competitive coding.
We want to be as language agnostic as possible. We're going to teach things in Python because it's easier to see implementations in Python, but we say, screw Python, please use C++ instead.
I think what Arif was trying to say is that Python is really just basically pseudocode, and I think it's pretty simple for everyone to understand. So we're teaching it, but just make sure, like, take in mind with these, like, just take in consideration of what we're telling you, because if you're going to go competitive coding, this is going to matter. Like they do have some added time basically for Python, but it's still recommended to use other languages other than this one. Or you can import libraries that have a better implementation of sets.
Yeah. So so Python does a bunch of its own things under the hood without really telling you. As you can see, it sorted and it kind of sorted it by itself, and it will maintain this sorted order indefinitely. I think that that's really important to know about. So while this can be pretty useful in actual problems, you have to keep it in mind in case you don't want this behavior. So basically what we're saying about Python versus C++ versus anything else is that Python is great for learning, and Python is also okay for using in competitions. It's just that C++ is more, I guess you could say, has less surprises. In addition, it's also faster, although that is not as important in most competitions. C++ is and always will be faster than Python. So this is the set implementation in Python. In Python, if you want to do a set statically, so I can also make a set like this, like 1, 3, 5, 7, things like that. That is a set. Note that it uses curly braces instead.
Perhaps we should go over tuples right now, because that's also like very easy to show in code.
Sure. So tuples are basically, I guess you could call them pairings of, or not pairings, but associations of a bunch of different data structure or data types together. For example, going through X, suppose we wanted to print out every single value in X, but also the position it has in X. So to print out every single value of X, we could do for I in range, something like that. Now, this is so that will print out everything in X. Now, suppose that you didn't want to use this kind of notation. In Python, I guess you could, or a good way to do this would be something like this, where this is a tuple, meaning that it is a set of 1 or 2 or more values that are like kind of associated together. It's basically going over, instead of instead of being I through the indexes of X, it's going through the enumeration of X. Now, what that means is that if I were to print something like this, as you can see, oh shoot, did I do something wrong? Should not have these. No. No, this is why. This is supposed to be X. Yep, there we go. So basically, what this means is that it's enumerating over X, which means that it's associating a index with each X. So you could think of what this returns. So the problem is when we actually try to print out enumerate X, you can't actually, oh, sorry. you can't actually see what it is because it's its own object. It doesn't really, it's a generator in Python. And I'm not going to get into what a generator is, but basically what this is internally returning is it's returning for each value of x, it's returning something like 1, 3, or 0, 3, and then it will return after that, it will return the next value, which would be the index 1, and then 4. As you can see, 4 is that index at x, and then index 2 and 1, etc. So that is basically a tuple because it's returning or it's using 2 or more values together. This isn't really a great example of tuples in general, but I think it's important to know that they exist. I think we'll also be going over that on Thursday, right? We won't be going over implementation, but maybe usage, right? Yeah. Okay. So moving on, I was finished with sets. So now maps. Maps are really, really important. In maps, dictionaries are in Python rather, dictionaries are actual maps. So basically, a map is a key value pair list. Each key corresponds to the value that it contains or that it's associated with. And each key is can be thought of as a unique identifier to retrieve that value. So if each value was in a room behind a lock, you could think of each key as the literal key to unlock that room to get that value. Now, you could think of a map as a simple array, and instead of having a data type of int or string, it would have a data type of special object, which is a key value pair. So what I mean by this is that it looks very similar to an array. So here we have the lightsabers map, and each key is here we've represented each key as name, and the value is the color of that character's lightsaber. So what we have here is with the key of Yoda, we have the value of green. Key of Luke has the value of blue, and so on and so forth. In lots of languages, we use this colon to associate keys and values. I think that's used in several, I don't know about all languages. Well, obviously not all languages, but many languages do use this kind of syntax, very similar to what Python has here. Now to access values in a map, it would be very similar to accessing values in a array, where instead of using an index value, we use the key value. So this is accessing lightsabers with the key Luke. And at that key, we can see it's blue, so it prints out blue. Now, if I change this to something like Mace Windu, this will be purple. Now, if I try making this something that doesn't exist in that array, that will give me an error, as you would expect. It gives me a key error. Now, in Python, as I mentioned, these things are called dictionaries. But an important thing to note is that there are implementations of dictionaries which have a default value for every key, and that would be called a default dict. And for example, if I had a default dict where everything here was was defaulted to value of, let's say, no lightsaber, something would be that's not explicitly defined here would have that default value. So this would return default no lightsaber. And as I talked about before, about hash sets and hashes, we're not going to talk about hashes in detail right now, at least. Maybe after the lesson, if you guys are interested, I can go over it. Carlos and I and Arib might go over it a little bit. But all you need to know really are hash maps are maps that are hash based. Really simple, pretty self-explanatory. And that comes with all the O of 1 access time goodies that it has. So as far as today's lesson goes, that's pretty much all we have. I guess if we have any questions, you can go and ask right now in the chat, unmute. Yeah. And if you don't have questions, I guess we can go over some
big O notation problem, just like some analyzing some problems, big O notation.
Okay.
But
so now I'll ask, is it required to make multi-dimensional arrays in grid-like form, or is it fine to put it all in one line? So that's kind of a syntax question, right? This is basically, this can be done like this. I put it in the grid form for easier visualization. It doesn't actually have to be in that grid form. So what you can write is very, very, very flexible, especially in Python. I guess the main thing is that, do you want it to be easily readable? Then you can keep it in grid form yourself. Many times you won't actually define sets and maps and etc. All these data structures explicitly like we have. Instead, you'll be taking them from the input of the problem. Yeah, good question. If there is
if you have any question, honestly, like we want you guys to understand the concepts behind this. If you have any questions about the concepts, just ask away. I think it's pretty important just to understand these data structures.
Yeah, if not, I can stop the recording and we can move on to other things. Yeah. All right.